Welcome back, guys. We're going to be moving on to part B of our surface area lesson. And in this section of the video, we're going to be talking about the surface area of pyramids, cones, and spheres. As well, we're going to look at unit conversions and dimensional changes. So before we get into the actual calculations of the surface area, we're going to take another look at the relationship between pyramids and prisms. As I mentioned in the last video, one of the objects or a pair of objects that often get mixed up are pyramids and triangular prisms. So we're going to take a look at these. As I move the shapes in, you're going to see whether they belong or not belong. And so the first one is a yes. The next one is a no. And as I start to move these in, I want you to ask yourself, why are they yeses and why are they nos? And so we have a yes. We have another yes. A no. A no, a yes, and a no. Now, hopefully what you noticed as we were going through these is that the yeses are all examples of pyramids. Now, we do have a cone in there, but the cone behaves very similarly to a pyramid. All of these come to a point, whereas on the other side, these are all examples of prisms. Now, the ones that sometimes get mixed up are the triangular prisms. Notice that with a triangular prism, we have two faces, the two triangles that are opposite each other, separated by rectangles. So this is a triangular prism. Similarly, down here we have our triangle as our base, separated by rectangles. None of these objects come to a point, whereas with the pyramids, we have our base, and then it comes to a point. So really important that we don't mix up triangular prisms and pyramids. So this would be called a rectangular pyramid, a triangular pyramid, and here we've got 1, 2, 3, 4, 5 sides, so a pentagonal pyramid. Now you could think about this as a circular pyramid, but we call a circular pyramid a cone. All right, so let's start off with surface area of pyramids. First of all, it's important for you to know that there are different kinds of pyramids, as we just talked about. With a square-based pyramid, my base is a square, and with a rectangular pyramid, my base is a rectangle. That means my lengths and widths are not the same size. And with a triangular pyramid, my base is a triangle. All right, now there is a formula for the surface area of a square-based pyramid, and that would be 1/2 times the slant height times the perimeter of the base plus the area of the base. Now, there is that formula. I don't often use it because it only applies to our square-based pyramids. Instead, I have a tendency to just draw the nets. Now, when we're working with surface area pyramids, it's important that we know our slant height. All right, so our perpendicular height, we sometimes have to use to find our slant height. So often we have to use Pythagorean theorem, but the perpendicular height is more applicable to volume. The slant height is what we need because as that if I were to unfold this pyramid, as this piece tips down, it's the slant height of the pyramid that becomes the perpendicular height of the triangle. All right, so we're going to take a look at our first example here. We've got a pyramid, and this is a rectangular base pyramid because our lengths and widths are not the same, so it's 12 by 8. Now, drawing my net, I would start off by drawing the base, which in this case is 12 by 8. And then I picture this unfolding from my point, and it's almost like peeling a banana. My opposite triangles are going to be the same size. And the slant height of my pyramid becomes the perpendicular height of my triangle. So this now has a height of 12, and this one here that has a length of 12 has a slant height of 10. So again, that becomes my perpendicular height. Now again, as we're doing these, I've mentioned this in the last video, as you're doing these, as long as you have your dimensions labeled and you put your areas in there, I'm okay with that. You don't have to show me every single formula when we're just doing basic area calculations of triangles and rectangles. So 12 times 8 is 96. I have 8 times 12 divided by 2, or 1/2 base times height. So 1/2 times 8 times 12 is 48. Opposite triangle will be the same size. And then I have 60, and I have 60. And when I add all of those together, my total surface area will be 312 meters squared. Because this one rounds off nicely, I just left it as 312. If I had some decimals, typically I would round to the nearest tenth. All right, so I want you to take a look at these 4 pyramids down here. The question asks you to calculate the surface area of at least 2 of the following pyramids. I want you to pause the video, try some of these on your own, and then come back and check your answers. All right, now taking a look at our first pyramid here, this happens to be a square-based pyramid, so we can use our formula 1/2 times slant times the perimeter of the base plus the area of the base. And so we have 1/2 times 34 times 128, because 32 times 4 would be 128, plus 1024, because 32 times 32 is 1024. And that gives me a surface area of 3,200 inches squared. Taking a look at our next pyramid here, we have a rectangular pyramid, so I can't use that formula. I have 10 by 20, so my area of my base is 20 by 10. And then I have 2 triangles that have a measurement of 10 by 18. So 10 times 18 times 1/2, or 10 times 18 divided by 2 times 2. Essentially, the 2 and the 1/2 cancel each other out. Will give me the measurements for those 2 triangles. And then my other triangles will be 1/2 times 20 by 15.8 times 2. And that will give me a surface area of 696 centimeters squared. Now, taking a look at our third pyramid, this one doesn't give us a slant height. Instead, we're given a height of 18 centimeters. We know that it's a square-based pyramid, so we have 10 by 10. And so in order to find my slant height, I have to use Pythagorean theorem. And so I'm going to have the square root of 18 squared plus 5 squared, and that gives me 18.68. Again, on my calculator, I'm going to keep that exact. So if I type that into my calculator, I would have the square root of 18 squared plus 5 squared. Now, because this is a square-based pyramid, we can use that formula 1/2 times slant times the perimeter of the base plus the area of the base. You could draw a net. You could set it up the same as pyramid number 2. But the first important piece is that we start off by finding that slant height. And so I've got 18.68 and so on. I'm going to keep that number exact. So I'm going to go 0.5 times second answer. I'm going to bring that answer forward, times 40 plus 100. And that'll give me a surface area of 473.6 centimeters squared. All right, now taking a look at our last pyramid here, this one would probably be the most complicated that you would see. I have a rectangular pyramid, meaning my lengths and my widths are not the same, and I'm not given any slant height, so I actually have to find 2 different slant heights. So starting off with the side that's 6 inches, in order to find my slant height, I'm going to have to sketch my triangle. Now these can get tricky too, because we're trying to visualize them in 3 dimensions. And so coming out this direction here is half of 5, which is 2.5. And I have a height of 9. So using the square root of 9 squared plus 2.5 squared, I get 9.34. Again, that's a rounded number, so I'm going to have to try to keep it exact on my calculator. And then for the other side, I have another line coming out here. This will be a length of 3, and my slant height here is what I'm looking for, and my height is 9. So the square root of 9 squared plus 3 squared gives me 9.48. And then again, if I wanted to do this on my calculator, I would start off by typing in those numbers. So second square root, 9 squared plus 2.5 squared. Because mine's an older calculator, it might be easier for me just to type out those decimals. And then 9 squared plus 3 squared. Now, setting up all of my work, I've got the area of my base, which is 6 by 5. And then I have 1/2 times 5 times my slant height of 9.48 times 2. Because I know these cancel, I might not even have to put them in my calculator. I could just put 5 times 9.48 plus 1/2 times 6 times 9.34. And so typing this into my calculator, I'm going to have 6 times 5, which I know is 30, plus I'm going to have 5 times 9.48. So I can write that as 5 times, or I can just use brackets. Again, because that's my last answer in there, I can just type second answer. And then I'm going to add 6 times, now because I have an older calculator, it might be just easier to type this out. Put that in, and I end up with 133.47 or 48, which rounds to 133.5. So again, making sure those numbers stay exact on your calculator. All right, so next we're going to move on to the surface area of cones. And like I said before, cones are kind of like a circular pyramid, and these ones do have a formula. And so we're going to have the surface area of a cone is pi r squared plus pi rs. And just like when we talked about cylinders in the last video, it's really important that you understand where this formula is coming from. So if I do a quick sketch of a net for a cone, I have the circle piece, and then I have sort of this curved surface, which almost looks like a curved triangle. And when I fill in those pieces, a circle, the area of a circle is pi r squared, which means the area of this section is pi rs. So the circle is pi r squared and the curved space is pi rs. That's important because if I'm dealing with an application question where maybe the circle isn't relevant, I would cross off that part and not use that section of the formula. So our first question here, we're asked, what is the surface area of each of the following cones? So we're going to start off with our formula, pi r squared plus pi rs, and we'll substitute in what we know. So we have pi times 5 squared plus pi times 5 times my slant height of 8. Again, if you're not given your slant height, you might have to use Pythagorean theorem to find it. But in this case, we're given what we need. So 204.2 inches squared. And again, this can be done on your calculator all in one step. Now for the next question, we're asked for the surface area of this cone. We're given the diameter of 6, meaning that the radius is going to be 3. And we're given a height of 10, but not a slant height. The first thing we're going to have to do is find our slant height. So we have a height of 10, we have a radius of 3, and we're looking for that slant height. So our slant height is going to be 3 squared plus 10 squared, all square rooted. And if we put that onto our calculator, we're going to get 10.44. Again, that's a rounded number. Now, moving on, this is the surface area of a cone. And if this was just some regular cone like the one beside it, we would just do pi r squared plus pi rs. But we know that with an actual cone, like an ice cream cone, there is no top on it. So our formula is SA equals pi r squared plus pi rs. But because there's no top, we can cross that part off. And our surface area just becomes pi r times the slant, which means we're going surface area is pi times 3 times that 10.44. And so our surface area is 98.4 centimeters squared. All right, now taking a look at our calculator, that would give us that first step of 3 squared plus 10 squared, all square rooted, would give us that 10.44. We're going to multiply that number by pi and by 3, and we have 98.39 and so on. That would give us 98.4 centimeters squared. All right, so I'm going to get you to take an opportunity to try these practice questions. You're being asked to calculate the surface area of any of these two, and this should say cones, not pyramids. But I want you to pick at least two, pause the video, try them on your own, and then come back and check your answers. All right, so our first example here, we're not given a slant height, so we start off right away using our 8 and our 6 to find our slant height of 10. That would be 10 centimeters. And then we plug that into our formula. So pi r squared plus pi rs will give us pi times 6 squared plus pi times 6 times 10, which gives us a rounded answer of 301.6 centimeters squared. Moving on to our next example, in this case we are given our slant height and we're given the diameter. So if the diameter is 20, that makes our radius 10. So we have pi times 10 squared plus pi times 10 times 39 gives us a surface area of 1,539.4 feet squared. Once again, we're being asked to find our slant height first, so we use the 13 and the 5 to find our slant height of 13.9. We substitute that into our formula, pi times 5 squared plus pi times 5 times 13.9 will give us a surface area of 297.3 centimeters squared. And our last example, once again, we have to find our slant height. So we use the 3 and the 4 to find our slant height of 5 meters. Substituting into the formula, we have pi times 3 squared plus pi times 3 times 5 will give us a surface area of 75.4 centimeters squared. Now, taking a look at an application question, we're told that a farm equipment manufacturer in Yorkton, Saskatchewan has decided to construct a grain bin using galvanized steel. And the question is, how much steel is required to construct the grain bin as shown? And we're asked to express our answers to the nearest hundredth of a square foot and not to include overlap of the steel sheets where they're fastened together. All right, so taking a look at our measurements here, first of all, for the cone section, we're going to need to know our radius, which is this length right here. We know that the diameter is 19 feet, so that's going to make this 9.5 feet. So half of 19 is 9.5. And then we also need to know our height here. Now, the height here is 21, and the height from the base to the top of the grain bin is 25, so that makes this height here 4 feet. So when we're working with our cone section, we're going to have to find this slant height right here. And so to do that, we're going to have our triangle. We have a length of 9.5 and a height of 4. So our slant height will be the square root of 9.5 squared plus 4 squared, and that gives us 10.3 feet. Now again, we're going to keep that exact on our calculator, so I'll go through the calculator portion at the end. Now, for our conical section or conical section here, when we're looking at the amount of galvanized steel being used, we're not going to be using the circular portion. So while our original formula is pi r squared plus pi rs, we aren't going to be using the pi r squared portion. So we're just going to have pi r times the slant height. So our surface area will be pi times the radius of 9.5 times our slant height of 10.3, which again, we're going to keep exact on our calculator. And so that surface area measurement gives us 307.64 feet squared. Now taking a look at the cylindrical section, again, our top circle is going to be covered up, so that's going to adjust our formula. And then we have the lateral face, and we have no circle on the bottom either. So calculating this out here, we're going to have our original formula of 2 pi r squared plus 2 pi r h. And because the circles are not included, we're going to cross those off. So we're just going to have a surface area of 2 pi times radius times height. So our surface area here is going to be 2 times pi times the radius of 9.5 times 21. And calculating that out, we're going to have 1,253.495 feet squared. Now, adding those two amounts together, we've got 307.64 plus 1,253.495. And again, we've kept these numbers exact on our calculator. We're going to have 1,561.13 feet squared. Now, the assumption that I've made here is that we're not going to have galvanized steel on the floor. Typically, you're thinking about a cement pad or this being put on top of a cement pad. All right, so let's take a look at what this would look like on our calculator. We start off by finding our slant height. So second root, 9.5 squared plus 4 squared gives us that 10.3, and we're going to keep that exact when we multiply by our 9.5 and our pi. So times 9.5 times pi gives us 307.64. Now, because I've already done all of the work, I'm just double checking my answer. I'm just going to add this automatically to the 2 pi r h. So I'm going to add 2 times pi times the radius of 9.5 times 21 gives me my exact answer of 1,561.13 feet squared. Now notice, if I had just been rounding here, if I had just gone 307 307.64 plus 1253.495, I would have had 1561.14. So it's really important that we avoid those rounding errors by keeping everything exact in our calculator. If I had just used my rounded answers, I would have been off by a decimal point. Moving right along, we're going to talk about surface area of spheres. Now, this also is an object that comes with a formula, and with some of my classes, when we have time, we actually work at deriving this formula in class. And believe it or not, you can just do it with some oranges. So if you want to try this out at home, get yourself navel oranges work best. Slice the orange in half. So we're going to have our orange here. You're going to slice it in half, and then you're going to grab a piece of paper and you're going to put the orange on the paper and trace a bunch of circles. Trace as many circles as you think you might need to fill them up with orange peels. Now, at that point, you're going to take these peels and you're going to start peeling them off the orange and puzzling them together onto your page. And as you do that, you're going to find that you can fill a certain number of circles exactly without overlapping or having a bunch of gaps with your orange peels. You should be able to fill a certain number of circles. And that number of circles is 4. So if I were to take all of those orange peels off and start puzzling them in, I would actually be able to fill in 4 circles almost exactly. I've done this experiment with a number of classes over the years. We always come up with 4, so I'm pretty confident that it's always going to be 4 circles. Now, my formula then is 4 pi r squared, because the surface area would be represented by those orange peels, and that surface area filled 4 circles. The area of a circle is pi r squared, so 4 circles would be 4 pi r squared. So this is a formula that I have had memorized for a long time because I just think about 4 circles. I think about oranges and 4 circles, and I know that the formula is 4 pi r squared. All right, so I want you guys to actually pause the video, try these next 2 questions on your own, and then come back and check your answers. Taking a look at these 2 questions, we're asked to calculate the surface area of each sphere. So we use our formula 4 pi r squared, we substitute in our radius of 3, and we get a surface area of 113.1 feet squared. And then our second one, we have 4 pi times 6 squared. We're told the diameter is 12, that means our radius is 6. And that gives us a surface area of 452.4 centimeters squared. Now, taking a look at our last example here, we're told that an official Major League Baseball has a diameter of 7.4 centimeters, and correct to the nearest tenth of a unit, we're asked what amount of leather is needed to cover the ball. So sometimes when we're given these questions, we're not told explicitly whether it's surface area or volume. Because we're doing a surface area lesson, it kind of gives it away. But it's important to understand that when we're talking about the amount of leather needed to cover the ball, that this is a surface area question. So we're going to start off with 4 pi r squared. We're told that the diameter is 7.4, so that means our radius is half of that, which is 3.7. And so we're going to have 4 pi times 3.7 squared, and we'll have a surface area of 172.0 centimeters squared. All right, so we're going to move away from calculating surface area and we're going to move on to converting area units. So we talked about conversions in a previous lesson. Now we're going to look specifically at converting units when it's related to area. And so we can do that using something called unit analysis. If we had, for example, a rectangle and we were given the measurements in centimeters. So for example, 10 centimeters by 15 centimeters, and then we were asked to convert this to inches squared. Well, we could do that one of 2 ways. We could find our area first and then convert it, or we could convert each of these linear measurements first and then calculate our area. So there's 2 different ways to do it. But if in the case of this question here, we're already given the measurements that we have to convert, we can use unit analysis. So the question says the area of my carpet space is 216 feet squared. So we're given 216 feet squared. And the carpet is sold by the square yard. So we're asked how much is this space in square yards, and signed carpet confusion. So we're going to be multiplying, and we want to start off with feet squared and end with yards squared. but that means we have to cancel out the feet twice. So you notice that we're going to have our conversion units twice here. Now, if we go and look at our conversion chart, we know that 1 yard is equal to 3 feet, or 3 feet is equal to 1 yard. So we start off with feet squared. We want to cancel feet, so we have to cancel feet and then cancel them again. And that means we're multiplying by our conversion factor twice. And so we have 1 yard to 3 feet and 1 yard to 3 feet. So we're going to have 216 times 1/3 times 1/3, or we could think about it as 216 divided by 3 and divided by 3 again will give us 24 yards squared. Now, there is a shortcut. Notice that if I was just going from feet to yards, I would divide by 3. If I take 216 and I divide by 3 squared, I will also get 24 yards squared. And so if I'm converting my area units, I can multiply or divide by the conversion squared. So square units, squared conversion. So taking a look at the example that I have here, if I wanted to calculate my area and then convert it, 10 times 15 is 150 centimeters squared. And 1 centimeter is equal to 0.3937 inches. So if I want to go from centimeters squared to inches squared, I would multiply by 0.3937 squared, because again, I'm using square units, and I would have 150 times 0.3937 squared, which would give me 23.25 inches squared. Now, let's just check to see if that works. If I wanted to convert 10 centimeters to inches, I would have 10 times 0.3937. That's 3.937 inches. 15 times 0.3937 is 5.9055 inches. And if I multiply those two together, I get 23.25 inches squared. So again, if I want to convert area units, I have to multiply or divide by my conversion factor squared. All right, so we're going to look at one last piece, and that has to do with dimensional changes. In other words, how is an object affected, or how is the surface area affected if we change just one length, if we double all the sides or triple all the sides? And so we're going to use an app to do this. Taking a look here, we're going to look at some specific examples. We've got a rectangular prism on both sides, and we want to look at how surface area is affected in both cases. So I'm going to work through some questions that are included in your notes. So the first one says, how would the surface area change if one side length was doubled? So we're going to have measurements here. We've got 5, 5, and 5, and we're going to double one of the side lengths. So instead of having 5, 5, and 5, we're going to have 5, 10, and 5. And if you take a look, our original surface area was 150 meters squared. Our new surface area is 250 meters squared. And that means it's increased by 100. But why has that happened? Well, when we increased our length to 10, when we doubled that, then our length times width and our length times width both doubled. So we have 10 times 5, 10 times 5. That now becomes 50 plus 50 instead of 25 plus 25. And when we look at our length times height and our length times height, instead of having 10 or 5 by 5 and 5 by 5, we now have 10 by 5 and 10 by 5. In other words, we've increased by 100. Now that's based on those specific measurements. If I wanted to change my dimensions here, I've got 3 by 3 by 3 and then 3 by 3 by 6. Notice now 90 minus 54 is not 100, but it's still been changed based on our dimensional changes. So we've got 90 minus 54 is 36. And let's take a look at why that happened. So we have 3 by 3 and 3 by 3, but now our 3 by 3 has become 3 by 6. So instead of 9, we have 18. When we get back to the notes, we'll take a look at the formula and how the formula is actually affected. Now our next question we're going to take a look at is how the surface area would change if all of our dimensions were doubled. So instead of just doubling one dimension, we're going to double all of them. So we've started off here with 3 times 3 times 3. And on the other side, we have 6 by 6 by 6. And so notice here that we have a surface area of 54 and a surface area of 216. And if I divide 216 by 54, I get 4. So our surface area has become 4 times bigger. Let's try another example. All right, so our first prism here, we have measurements of 5 by 5 by 5, gives us a surface area of 150 meters squared. When I double all of my dimensions, that makes it 10 by 10 by 10, with a surface area of 600. 600 divided by 150, 4 times bigger. Now let's take a look at one more example here where our dimensions are not all the same size. So I have a rectangular prism that measures 2 by 3 by 5, gives us a surface area of 62 meters squared, versus a rectangular prism where all of the dimensions have been doubled. So now we have 4, 6, and 10, and we have a surface area of 248 meters squared. Well, if I take 248 and I divide by 62, once again, the surface area has quadrupled. All right, so what happens if we triple all of our dimensions? Here we have original rectangular prism is 3 by 3 by 3, gives us a surface area of 54. And then when we triple all of our dimensions, we have 9 by 9 by 9. And if we take the surface area of 486 and divide by 54, we have an increase of 9 times. So the surface area is 9 times bigger. If the dimensions aren't the same, we still have the same outcome. So we have measurements here of 2 by 2 by 1 gives us a surface area of 16. And when we triple all of our dimensions, we have 144 divided by 16. Once again, 9 times bigger. Now, as one last example, let's take a look at how the surface area would change if the area of the base was doubled. So we have here 2 by 2 by 6. The area of our base is 4. And then to double that, I've made one side 4, so now the area of the base is 2 times 4. Our height remains the same in both cases. If we look at our correlation here, we have 88 and 56. Well, 88 divided by 56 is 1.57. If I subtract them, I have a difference of 32. If we try another measurement here, let's say we've got a base area 1 by 1 gives me an area of 1. To double that, I could go 1 by 2. Checking our correlation, we have 40 divided by 26. The decimal would be 1.54, so that's not the same as before. And there doesn't look to be a significant correlation when we just double the area of the base. So let's take a look at those questions one more time, and we're going to look at how the formulas are impacted. So taking a look at the formula for the surface area of a rectangular prism, we have 2 times LW plus 2LH plus 2WH. The question asks us about doubling one side length. So let's say I double the length. Well, that is now going to double this measurement, and it's going to double this measurement. So our formula goes from being 2LW plus 2LH plus 2WH to 4LW plus 4LH plus 2WH. Now the next question, we were asked how the surface area changed if all dimensions were doubled. Well, we did a few examples and we found out that in all cases it became 4 times bigger. But why is that? Well, surface area represents units squared. And when we're doubling, that means we're multiplying by 2. Notice that 2 squared is 4. And so then we were asked how the surface area would change if all the dimensions were tripled. Well, this ended up becoming 9 times greater. Well, let's look at what we know. Surface area is units squared, and tripled is times 3. Note that 3 squared is 9. So what if I had quadrupled? Well, quadrupled would be times 4. Surface area would be affected in that it's 4 squared, so 16 times greater. And then the last question, we looked at how the surface area would change if the area of the base was doubled, and there was no rule or correlation. But again, when we get into volume, we will notice that this one does have a relationship. All right, so one last example here. We're asked, how does tripling the radius affect the surface area and volume of a sphere? Now, we haven't got into volume yet, but I want you to use what we already know to predict what it might be. So when we're looking at surface area here, we have a radius of r and a radius of 3r. Tripling means that we're multiplying by 3. And if we're talking about surface area, we're talking about units squared And if we're talking about volume, which we haven't got into yet, we're talking about units cubed. So how will surface area be affected if we triple it? Well, 3 for tripling, squared for square units, 9 times bigger. Now, using what we've already seen, we can probably predict what will happen to volume. Well, with volume, we're tripling, so it's still 3, but units are cubed. So we're going to have to multiply by that conversion factor 3 times. So 3 cubed would be 27 times bigger. All right, so most importantly, what you want to get from this, when we're converting our area units, we have to square our conversion factor. When we're doubling, tripling, quadrupling, or anything to all of our dimensions. So if I was maybe taking all of my dimensions and multiplying every dimension by 5, the surface area will be affected by 5 squared. 5 because we're multiplying all of the sides by 5, and squared because it's surface area and we have units squared. If I'm tripling, 3 times 3 squared is 9. If I was doubling all of my sides, 2 squared is 4. So our surface area will always be affected by the number that we're multiplying all of our sides by, squared because it's units squared. All right, that's all I've got for you guys today. Have a great day and we'll see you soon.